In this video, we're going to talk about three basic principles of visual perception and when we visualize things, how humans interact with those things. So there's going to be a few of these kind of brain teasers or optical illusion kind of things that we go over in the next few videos. But what is your brain telling you about those five small rectangles? 1, 2, 3, 4, or 5. Which one is the lightest? Now, don't think about it. Which one is the lightest according to what your brain is telling you? Now, many of you may have seen something like this already and realized that all five are actually the same color. But almost everyone says that number 5 here on the right is the lightest. A few people every once in a while say 3, and I'm not quite sure why. But the people on the right, usually almost everyone, 98% of the people say the one on the right. And why is that? It's because our eyes, when we look at something, don't evaluate it and say, oh, that's RGB value XYZ, or that's this particular color blue. That's why when you go to the paint store and you see all the different blues, it's like, how different are these really, right? Oh, this one's a little darker. But if you held up any one of maybe 3 or 4 color blues next to a dark color black, one at a time, you wouldn't necessarily be able to tell which blue was the lightest or the darker. Only when we compare a color to another color do we see this relative difference. And so the eye is basically comparing this small rectangle, which is exactly the same color in all 5 counts, with its surroundings. And it's showing that, well, the difference between these two is much less than the difference between these two, so this must be relatively lighter. And so what we see with our eyes is relative differences. Now, this is going to become a mantra of what we talk about in this class, which is compared to what? We help people gain insight through visual representations of data by comparing something to something else. Now, because of that, we have to be very careful about the way that we use color and distance and location and placement in order to make sure that we aren't actually sending a signal that we don't intend to. So if we're going to use a color, we want it to have meaning. If we're going to use a position, we want it to have meaning, because we don't really perceive absolute location, absolute distance. We just see nearer or far, or more near, more far, higher or lower, darker or lighter. We perceive relative differences. And this is an example you may have seen before. This is kind of a classic example. Again, thinking about it or looking at this, what is your brain telling you between square A and square B, which one is darker? Now, this is the one that always blows my mind because A is clearly darker, but that shadow is messing with our perception. And if you actually sampled those two squares, you'd find that they are literally the exact same RGB value. It's hard to believe, but it's really true. Just simply because it's relatively lighter or darker than what's around it, we are perceiving them as different colors in this one, but they're actually the same color. And I see that more like if I squint my eyes a little bit to try to hide what's around it a little bit, I do see that kind of darkens out to being the same color. But when you're looking at it, your brain is not going to tell you that, all right? So the second thing is that we can't attend to everything we see. Our brain is constantly trying to filter things out to say, not important, don't spend the time on that, it's not going to kill me, and it's not what I'm thinking about right now, forget it, okay? Now, differences and uniqueness drives attention. Let's take a look here at the next thing here. What is this a picture of? I'll give you a few seconds. What is this a picture of? Almost everyone will say rose. A few people say flower, but almost everybody says rose. Now, why do people say rose? Because this rose is a known shape. And my brain is overloaded with information that's coming in through my eyes. And so it says, I know what that is. That's a rose. I can forget about it. Now, if I told you there was a picture of a dolphin in this picture, you'd be like, what? It's a picture of a rose. But as soon as I show you this, and then I say, now look back up at the picture, you'll see the shape of this dolphin right here, right? So most people aren't going to pick up on that. A very few people who are super detail oriented do, but most people just never see that. And it's because your brain is trying to ignore stuff as much as it possibly can. So we have to make sure that we don't let the brain filter out what's important. We have to give the eye something important and different, either through a brighter color or a different placement on the screen or a different shape or something, so that the brain says, oh, that's different, I should really look at it. Now, the third thing is the problem of memory. Now, memory is extremely important in cognition, but memories are really quite bad. Taking a look at this picture, what is this a picture of? Now, almost everybody would say, well, it's a picture of a sphinx. Now, why would people say it's a picture of a sphinx rather than a picture of a tropical location or a picture of a couple of older people? It's because of the placement of the sphinx. It's in the center of the picture. It's dominating the size of the picture, and so it's what's considered important in the picture. Now, when you're looking at that picture, you're not attending to all the parts of the picture. Your eye says, what's the important part, and that's what I'm going to focus on. You did not go around all the parts of the picture and really attend to what was where. And so when you look at this picture, you say, yeah, it's a picture of a sphinx. But if I told you that this is not the same picture that I put up the first time, almost no people will be able to pick out whether I'm telling the truth or not. So I'm going to show you this picture and the other picture side by side. And I will tell you that right now, I'm still embarrassed to say, when I looked at these pictures side by side the first time, I looked at them for 10 minutes before I could pick out the difference, and I couldn't ever pick out the difference. I had to read what the difference was. So here's the two pictures. What's the difference? Now, it's not something silly like I've made the shadow smaller. It's nothing small. It's a major difference. And now you ought to be able to see it, that here behind the sphinx in this one, there's this shrubbery, but here there's no shrubbery. So that kind of leads us to understand this idea that we can't rely on people's memory when we are doing our visualizations. We have to present them all the things they need to make the evaluation on one screen, so that we don't have to rely on people's memory. Now, our working memory is very limited. Humans can hold between 0 and 7 chunks of information in their working memory. Now, that capacity rises during maturity and falls during old age, so we kind of start being able to hold 0 chunks, and we kind of end being able to hold 0 chunks. Unfortunately, the peak of your working memory performance is about age 25, and then it's all downhill from there. Now, the typical human can only hold about 4 chunks in working memory, and the typical human can only pay attention to 1 chunk at a time. Now, how do we reduce this cognitive load so that people don't have to use their working memory? Well, we've always used artifacts to reduce cognitive load. And just think of a simple multiplication problem, 57 times 48. Now, some people can do this in their heads, but most people can't. And the way that we take care of that problem of being able to do it, not being able to do it in our heads, is we write things down. And we have a whole set of operations where we multiply 7 times 8, it's 56, we put the 6 there and the 5 up there, we multiply, and then we drop it. We forget about it. We don't have to remember that anymore because we've written it down. Then we multiply 8 times 5, 8 times 5, and we add the 5, so we get to 45, so 456, and then we drop it. That's 7 times 4 equals 28, and then 5 times 4 plus the 2 is 22, and then we add this stuff up, and we get 2736. Now, at every point in time, our brain was only using 1 chunk. What's the thing that I'm multiplying or adding right now? And we were dropping the other things into the artifact. And what we're going to be doing with our excellent graphs is that we are going to be providing an artifact that does not rely on the human to have to evaluate things and make calculations in their brains. We're going to be providing them with an artifact that helps them to make comparisons in a single chunk at a single time, right? And so we want to show the data that allows us to make comparisons. We want to illuminate the differences that make those numbers interesting. and we don't want to require the user to remember or calculate. This is just kind of a foundational set of things. They're going to come back again and again in this course in different forms and different flavors. And so that's it for this video. Talk to you later.